It was 4 a.m. on November 25th atop Hawaii's dormant Mauna Kea volcano, and the chill in the mountain air was sharp enough to wake even the most groggy astronomers. Despite the early hour and the thin, crisp atmosphere at nearly 14,000 feet above sea level, the excitement in the control room was palpable. The team had been preparing for weeks, coordinating international telescope schedules, aligning data streams, and ensuring that every piece of observational equipment was calibrated to perfection. The goal was singular: to witness one of the rarest phenomena in human history, the passage of interstellar Comet 3I/Atlas, an object traveling through our solar system from the depths of another star system, carrying within its secrets that may predate the very formation of our own sun. Though the process to view the comet had been expected to be painstakingly slow, filled with delicate adjustments and careful maneuvering of the telescope, it instead took far less time than anticipated. Within moments of powering up the main instruments, the comet appeared on the screen, a small, fuzzy, and seemingly unremarkable blob drifting against a crowded tapestry of distant stars, each pinprick of light a reminder of the vastness and complexity of the cosmos. On a second, specialized monitor, the comet's light was dissected into a spectrum, a barcode of rainbow lines stretching across the screen, each hue and intensity representing a different element or molecule evaporating from the comet's icy nucleus. Some of these lines were bright, almost screaming for attention, while others were faint, subtle whispers revealing the less abundant compounds. It was an ethereal sight, both mesmerizing and scientifically profound. This spectral fingerprint allowed astronomers to identify gases boiling off the comet, mapping its chemical composition in real time. The ability to observe such detailed information live was unprecedented, giving the global audience a rare glimpse into the dynamic processes occurring in a tiny, distant object hurtling through space at incomprehensible speeds. "This is some prime-time science happening in real time right now," said Bryce Boland, principal investigator of the ongoing study on 3I/Atlas, addressing an online audience that spanned multiple continents and time zones. He spoke with a mixture of awe and enthusiasm, fully aware that the moment being witnessed was historic. The session was hosted by Shadow the Scientists, an organization dedicated to connecting experts and laypeople alike, democratizing access to real-time scientific discoveries through virtual seminars. These events had become increasingly popular, bridging the gap between high-level research and public curiosity. In this instance, viewers could experience the thrill of discovery from the comfort of their homes, while sharing the same screens and insights as the professional astronomers stationed at the Gemini North Telescope. This telescope, perched atop one of the highest points in the Pacific, provided a critical vantage point with minimal atmospheric interference, enabling scientists to track the comet with unprecedented clarity. What the observers were truly seeing on the control room's monitors, however, went far beyond the mere existence of a comet. This was effectively a time capsule, a fragment of cosmic history encased in ice and rock, potentially older than the sun itself. It had drifted through the interstellar void for millions, perhaps billions of years, a silent voyager witnessing the birth and death of stars in alien systems long before our solar system even existed. Now, by sheer cosmic chance, it had passed close enough to the sun to enter the reach of our observational technology, providing humanity with a fleeting opportunity to study matter from beyond our solar system. Its close pass by our star, a glittering sphere that it had spent most of its existence observing from afar, offered invaluable clues about the behavior and composition of interstellar objects. Each speck of ice, each burst of gas, each jet from its nucleus told a story of its origin, a narrative written in the language of chemistry and physics. This encounter was not the Gemini Observatory's first observation of 3I/Atlas. Back in August, when the comet was still on its inward trajectory toward the sun, the southern half of the Gemini Observatory, located in Chile and known as Gemini South, had captured early images and spectra. These pre-perihelion observations documented the comet as its tail began to emerge, an extraordinary process that began in earnest as solar radiation warmed the comet's surface. Data revealed a distinctly comet-like structure, including a bright coma, the diffuse envelope surrounding the nucleus, and gas jets dominated by carbon dioxide and cyanogen. This chemical signature was particularly intriguing because it differed from the behavior of most comets originating within our solar system, which tend to release water vapor more prominently. The detection of such molecules suggested that 3I/Atlas had formed under different conditions, likely in a distant planetary system where the chemical environment varied significantly from our own. Such insights offered scientists an unprecedented window into the diversity of planetary formation processes across the galaxy, providing a tangible connection between distant star systems and our own backyard in the cosmos. By late October, the comet had already completed its closest approach to the Sun, known as perihelion, traveling at a staggering velocity of approximately 130,000 miles per hour, or around 209,000 kilometers per hour. During this phase, the comet's activity peaked, as solar heating triggered the sublimation of surface ices and released a mixture of gases and dust into space, creating a spectacular, albeit invisible from Earth, tail. Observations during this critical period were complicated by the comet's position relative to the Sun, as it quickly became hidden from Earth-based instruments. Nevertheless, numerous space-based platforms, including NASA's Mars Reconnaissance Orbiter and even the Perseverance rover, captured glimpses of the comet during its solar passage, providing complementary perspectives that enriched the overall scientific dataset. These combined observations allowed researchers to construct a comprehensive model of the comet's trajectory, composition, and behavior, offering insights not only into the object itself, but also into the processes that govern the evolution of interstellar visitors. Despite these remarkable achievements, the Gemini Observatory, anchored firmly on Earth, missed witnessing the comet's peak activity during perihelion due to the limitations imposed by its terrestrial location. Nevertheless, the team remained undeterred, eagerly awaiting the comet's re-emergence into visibility as it traveled beyond the Sun's glare. The recent observations atop Mauna Kea represented the culmination of years of preparation and coordination, a triumph of modern astronomy and international collaboration. In the control room, excitement mingled with reverence as astronomers and enthusiasts alike realized the significance of the moment. Each image, each spectrum, and each data point collected contributed to humanity's understanding of the universe, expanding our knowledge of the vast, interconnected web of stars, planets, and interstellar objects that stretch far beyond the confines of our solar system. The comet itself, while small and faint to the naked eye, carried profound implications. It challenged assumptions about the homogeneity of interstellar objects, revealed the chemical diversity present in distant star systems, and offered a tangible connection to regions of space that would otherwise remain abstract and inaccessible. Through these observations, scientists could test theories of planetary formation, refine models of cometary behavior, and even speculate on the potential for life-bearing materials to traverse the galaxy. The fact that such a relic of the cosmos had arrived at our doorstep, even briefly, underscored the dynamic and ever-changing nature of the universe. As Bryce Bolin and his colleagues guided the online audience through the live feed, viewers could appreciate the comet not only as a scientific subject, but as a symbol of cosmic continuity. Each photon captured by the Gemini North Telescope had traveled for untold eons, carrying within it a story that spanned both time and space. The interstellar journey of 3I/Atlas reminded humanity of its small yet significant place in the universe, bridging the gap between abstract scientific research and the innate human desire to explore, understand, and connect with the cosmos. The morning on Mauna Kea became more than just an observation session. It transformed into a shared experience of wonder, discovery, and intellectual curiosity, one that would resonate far beyond the brief moments captured on the screens. By the time the session concluded, the comet had drifted further into the void, continuing its silent journey through the stars. Yet the data collected would remain, a permanent record of one of the rarest events in modern astronomy. Researchers would spend months, if not years, analyzing every detail, from the composition of the gases released to the minute changes in the comet's trajectory, each discovery adding a new piece to the puzzle of interstellar phenomena. In that quiet, pre-dawn hour atop a Hawaiian volcano, a global audience had witnessed a cosmic visitor, and, in doing so, glimpsed the timeless dance of matter and energy that defines our universe.